So, ready for the next one?
Yes.
Okay, thanks. I'm going to rush through this one even quicker, but the basic idea is when you consider Stoiljkovich's theory applied to modern cosmology, there is a lot of problems, and you've got controversies because, as Dragoslav calls it, there's controversy with Newton's laws, because when you apply, which is an extension of Newton's theory, and there's far more to it than what Newton just had in his Principia. So this is Dragoslav, my friend over in Serbia, and this is Stoiljkovich again, and this is the Big Bang. In Einstein's relativity, it's space expanding in the Big Bang, but in the context of Newtonian physics, you're thinking of galaxies moving away from each other, and what I'm talking about is an update of Newtonian physics, and so it's still in the context of Newtonian physics as these objects moving outwards in the Big Bang. So, the first thing that really shocked me is acceleration is not always a force involved. I used to think that if you had acceleration, that would mean there's always a force. But when you've got something like a radar gun, you are tracking an object, traffic here, and you've got an error factor, and the error factor can be like an acceleration. So when you're looking at objects, you have what might look like an acceleration, but it's really this error factor, and this type of acceleration is not caused by force. So it's a cosine, called the cosine effect angle. Another picture of it. So if we apply that to galaxies, instead of trucks and cars, the galaxies can be thought of moving like these, outwards like this. And you've got this problem of an acceleration, what looks like an acceleration, but it's not really caused by a force. And this is part of the way of Stoiljkovich's thinking. It's all coming out from the Copernican revolution. What you see as physical reality is not what's really underneath at a deeper level, because based on observations you would say that the sun moves around the earth. You would see it rises in the morning, it sets in the evening, and so just based on observations you would say that. But because of Galileo and all that making a fuss, it was decided what you see is not the same as what's really going on. There's a deeper level to things. So here's the example of the two galaxies which we analysed. Measured speed of two galaxies are not equal pace. According to traditional Newtonian comprehension, Stoiljkovich distinguishes between absolute and relative movements, and that's the issue of there's a difference between relative motion and absolute motion. Our perceptions are relative motion, but underneath that, at a deeper level, is an absolute motion. And so it's illustrated by Stoiljkovich. Of difference between absolute and relative motions. So first is case one, suppose some point is moving by uniform absolute motion in the direction AB, and that some other point is moving by the same velocity parallel CD. If the beginning of movement, the distance between points was AC, and at the end of movement it will be BD equals AD. Each point has been moved by absolute motion, but the movement of one point to another did not exist, since neither the distance between them nor the direction has been changed. The points are in rest relatively, even if they moved absolutely. So you've got this problem of points being at rest, but you've got absolute motion. So next considers point case 2. If the second point is moved along to some other direction, CE. And it's also case 3. In order to analyse the relative movements more thoroughly and exactly, he wants to derive the mathematical expressions for the relative movements of two bodies at parallel and crosswise directions to explain these cases. So he sets up the maths for it. So when you're plotting these things, you get things like this. Effect of time on distance between a moving body and a motionless body. And then you've got a plot of the relative velocity. So he notes the peculiarities this leads to. So when you're building up the maths from all of this, you get in these equations, which is coming from Stoiljkovich's theory. And you sort of raise conclusions from these issues of this analysis, and you wonder if Hubble's law seems violated by this recession velocities analysis, and the accuracy of the measurements of Hubble's constant is also called into question. Consequently, the concept of the expanding universe is also called into question. And also you have problems with Newton's laws, Newton 1 and Newton 2. So you're asking your questions, should Newton's laws have to be modified? So basically an analysis of modern cosmology based on its theory of the Big Bang theory from Stoiljkovich's theory leads to maths like this, where you're analysing it from an extended Newtonian physics theory, and you're kind of saying it doesn't quite make sense from cosmology. Thank you.
Thank you, Roger. We've still got some time for questions for Roger.
Oh.
I have a question on part one.
Follow.
You showed a slide where you said that Stoiljkovich's theory gave you an oscillatory gravitational force relatively close to the object. Now, my question is very simple. What was the scale on which you predicted those oscillations, how close to the object did you have to get in absolute terms?
One of the criticisms of Stoiljkovich's on this theory is that he worked out the curve, but he didn't work out all the mathematics to go with it. And so it is sort of ongoing mathematical development. And I have a friend over in America, a physicist, who's actually worked out the scale of these things. He's shown that it does fit modern physics, what modern physics is finding sort of all these other false curves.
I mean, as long as the length scale is tiny enough,
Yeah.
it obviously doesn't violate what we know.
It's sort of like on a conceptual level that Stoiljkovich is looking at it. This is the idea of an object falling. It's sort of like eventually hits the ground, meets resistance, and doesn't fall in, or doesn't carry on any further.
If I may say so, he didn't necessarily say it was gravitational force. He said positive and negative forces.
Oh, well, that's another point.
He didn't necessarily say it was gravity at all. It could be other forces.
Okay, thanks.
Okay. Yeah, the problem with gravity from Newton is always attractive, and that then from the force curve which you had up, the force, which is gravity, it then reverses itself.
So
That
it
force
could be
curve.
including the exclusion.
Well, it could be including other forces like electrical forces and so on. Whatever cohesion forces.
Any further discussions? Then I would like to thank Roger. Let's give him one more hand. I would like to thank